Hi everyone, let's continue. Circulation and flux of a vector field F along a path C. Suppose the vector field represents a fluid flow. Then we are given a path C. You may want to analyze how the field is moving in different directions at a point in its domain. For example, you may want to measure how much the field points in the direction of the path, or maybe you want to measure how much the field flows across the path, i.e., in a direction orthogonal or normal to the path. So these measurements are called circulation and flux. So imagine so this picture, this is the curve C, and then our vector field looks like this. Okay? And then you want to measure what is the components of the vector fields that in the direction of the path C. Okay, so you want to measure how much the vector field points in the direction of C. Well, then this is circulation or flow. Okay, but instead, if you want to measure, what is the components of the vector field so you want to measure what's the components of the vector field that go across the C. Okay, then that is the flux. Okay, so flux measure how much the vector field go across orthogonal to C. Okay, so let's look at the definition. So circulation. Here, the dimension could be 2 or 3, okay? So for a vector field F, so because the dimension can be 2 or 3, so let's talk about 3 and then we just delete one dimension and then we can get R2. Okay, so suppose a vector field F is FGH in R3 and we have a closed, smooth oriented curve C, then the circulation equals F dot product with the unit tangent vector ds. Okay, so this is F dot product with the derivative of the displacements. Okay, so T is the unit tangent vector to C consistent with the orientation. So far so good, everybody. Okay, so geometric interpretation. Circulation measures the net rate, how much the field points in the direction of C. Okay, so this is C. So if this is a vector field, okay, let me make it here. So this is a vector field. We want to measure how much are in the direction of C. Okay, if the circulation is positive, then we have a net forward flow. Okay, so forward flow. If the circulation is negative, then this is the orientation of the curve, then we have a net backward flow. Okay, so intuitive way to think about it, if there is more fluid flowing along C in the forward direction, then this is then in the backward direction, okay, then this means circulation is positive. Vice versa, circulation is negative. So we add up the components of the force, the vector field, in the direction of the unit tangent vector T at each point. So far so good, because the unit tangent vector measures measure in the direction of C. Okay, this is C. This is the unit tangent vector. So far so good, everybody. Okay, and how about the other way? Flux. Okay, so here the dimension of flux, we have 2 dimensions. We also have the 3-dimensional flux, but it's not for a curve, it's for surface. Think about it. If we have dimension R2, then we have a curve. We can talk about, vector field in the same direction, or we can talk about vector field in the orthogonal direction, right? But if it's in R3, well, we have a curve, then we can have a vector field going in the same direction, but for the going across it, well, there is a lot of vector that is orthogonal to it. So the direction across the path in the space is not defined. But however, if it's in the space, if we have a surface, then we can talk about the vector field going across it. So yeah, so for surface in R3, we can talk about floods. But for curve in R3, we cannot talk about floods. Okay, that's why right now we're only looking at curves. So for the floods, let's only define on the dimension R2. Okay. So for vector field F in FG in R2 and a smooth oriented curve C that does not intersect itself, so it may or may not be closed. Then the floods. Okay, so we have the curve, right? This is the tangent vector. Oh, sorry. I want to use the pink color to denote the floods. Okay, so we have a curve, right? And we want to measure, so let's say we have this guy, so we want to measure how much vector field going across it. So that's why we want to find the component with the normal vector. Okay, so let's say if the curve is going forward, then the normal vector n is always pointing to the right hand side. Okay, we're in R2. Okay, then the flux is the path integral of f dot this normal vector n ds, and that is actually equals. Okay, how do we get this formula? Okay, let me explain here. So this is how to find the normal vector. Well, t is the unit vector tangent to C lies in the xy plane, so its z component is 0 when we view it in the space. Then we can define t be tx, ty, and and 0. Okay, let k be the unit tangent vector points in the z direction. Well, then we can define n to be t cross k. Okay, so this guy n will be perpendicular to the unit tangent vector, and it's also perpendicular to the k. K is the vector in the z direction, which means n is gonna be in the xy plane and orthogonal to t. Okay, so what is this guy? What is this cross product? So we have I, j, k, right? T is tx, ty, and 0, and then k is 0, 0, 1, right? So this guy is then we have I, and then we look at the minor of this submatrix, right? The determinant of this submatrix. We have ty times 1, so it's ty, and then we have minus j in the middle, and then we look at this guy and this guy, so it's tx times 1, so negative tx. And let's look at k. K, the minor is this 4, and g is 0. Okay, so our normal vector equals ty minus tx. Okay, so let me give you some example. Okay, so let me find a space here. Where do I have some space? Okay, let's use some space here. Suppose our t, let's say our t is 1, 2. Okay, so our curve look like that. T is 1, 2. Then what is n? Well, n is ty, so 2, and then minus tx. Tx is 1. Well, 2 minus 1, so 2 is like this, minus 1 is like that. So in this direction. So far, so good, everybody. Okay. And you can see it's like on the right-hand side of the curve. So what is geometric interpretation? Floods measure the net rate, how much the field flows across C, i.e., in the direction orthogonal or normal to C. So if floods is positive, it means more flows points to the right. If the floods is negative, then we have more flows points to the left. Okay? So intuitive way to think about it. If there is some fluid flowing to the right as the curve is transverse in the forward direction, then this means the flux is positive. Vice versa, flux is negative. And here we add up the components of F orthogonal or normal to C at each point of C. Notice that there are two unit vectors normal to C, hence we defined the n to be t cos k, okay? Then we can add up the components of F in the direction n at each point. Okay, so yeah, see this curve, we have, let's say this point, we have two normal vector pointing to the left or pointing to the right, and we picked the one pointing to the right. Notice that if C is a closed curve oriented counterclockwise, then the unit normal vector points outward along the curve. So think about it. Now, if we have a closed curve, closed curve oriented counterclockwise. Well then, pointing from the left to the right, it means, well, we're measuring the fluid that flows outward. Okay, so outwards along the curve. Okay, then the first integral give us outward flux across C. Okay, on the other side, if the curve is oriented clockwise, then the unit normal vector will be inward direction. Then we get an inward flux. So far, so good, everybody? So caution, this unit normal vector n is not the same as the principled normal vector. Okay, so do you still remember the principal normal vector? Well, that is the derivative of the unit tangent vector over the magnitude of that. Okay, so that's the t prime over the magnitude of t prime. Okay, so notice that n here, n points in the direction that the curve C is turning. So we might switch left and right. So we used capital N to denote the principal normal vector. Let me draw a path here so you can see the difference. What is n? What does n do? Okay, so n. So if the orientation of the curve is, I should point it out. So let's say this is the orientation of the curve, right? Then what is the direction of our small n, okay? Which is the unit normal vector that we define, it is t cos k. Okay, so it's always from the left to the right. So here we get this guy, this guy, this guy, this guy, and this guy, right? Always from the left to the right. But now how about our principal normal vector? Well, which color do you like? Do you like blue? Okay, the principal, so there's an extra word, principal normal vector, and we use capital N. Well, this is t prime over the magnitude of t prime. And it is the direction in which the curve turns. So here it turns to the right. So it's to the right. Here it turned to the right. But you can see at this point, it turned to the left. So it's changed. See, now it turned to the left. And here what happened? it turned to the right again. So sometimes at some points it could be to the right, at some points it could be to the left. It really depends on the path, in which direction the path is turning. So far so good, everybody? So they are different. So caution. They are totally different, so be careful with that. Let's continue. So let's look at this example. Find the outward flux across the unit circle with counterclockwise orientation for the following vector fields. Okay, so here I want to do both. I want to calculate the circulation and the flux. Okay, so let's see. So circulation, let's draw a picture. So here we have a unit circle. Okay, so C is the unit circle with orientation counterclockwise. And then what is the parameterization for it? We have the natural parameterization, that's cosine t, sine t. Right, everybody? And what is the circulation? Let's calculate circulation. What does circulation do? So here, this is the orientation, right? Circulation measures how much vector field points in the direction of C. Okay, so let's see here. So we have the line integral f dot dr, and what's r prime? R prime equals minus sine t, and this is cosine t. Right? And so we have the dot product. So we have t from 0 to 2 pi, right? F is xy. Xy is the same as cosine t, sine t. Dot product with minus sine t, cosine t, dt. Let me see. Can I move this guy? Oh, okay. Can I move this guy? Yes. Let me move this on the left, and I can have more space. All right. So that equals cosine t times minus sine t. We get minus cosine t, sine t, and here we have plus sine t, cosine t, dt. Ooh, what happened? We have them cancel out. So that is 0. Why is that? Well, look at this. Look at this vector field. What does this vector field look like? So this vector field xy looks like, so at a point there, so 0, 0 at a point 1, 1, and then it will get 1, 1. So this guy, the vector field looks like this. Then now you can see, wow, what is the component of the vector field in the direction of C? 0, because this vector field is actually orthogonal to the path, the unit circle. So far so good, everybody. So here the circulation is 0. Okay, now how do we compute the flux? Well, let's use a different color. Let's use pink. Okay, so in order to find flux, we need to find n. So what is n? Well, n, remember, is ty minus tx. What's ty minus tx? That is the second component of r prime or gamma prime, right? The velocity. So second component of the velocity is cosine t, and then minus, what's the first component of the velocity? Negative sine t, right? So this is the same as cosine t sine t. So far, so good, everybody? Alright. Then, what is the flux? Well, flux equals along the path C, F dots N ds. Well, that equals, so our t goes from 0 to 2 pi, f. So f is still cosine t sine t, dot our n is cosine t sine t dt. So far, so good, everybody? And what do we get? Well, that equals 0 to 2 pi cosine times cosine, so cosine squared, plus sine times sine, sine t squared dt. Ooh, that is 1. Integral of 1 is t evaluated from 0 to 2 pi. We use 2 pi minus 0 is 2 pi. Why is that? Well, because what's flux? Because this curve is oriented counterclockwise, then flux is from the left to the right, from the left to the right, from the left to the right, from the left to the right. Well, that's exactly where the vector field is pointing at. That's why we have the positive number. Positive, we have outward flux. So far, so good, everybody? Okay, let's look at the other picture. Okay. I should move this on the left so I have more space. Okay. Okay, on the other picture, we have a different vector field. So what does this vector field do? Let me, okay, change back to my color. Okay, so what does this vector field do? Suppose we have the point 1, 1, then we can see this is going to be minus 1, 1. So minus 1, 1 is right here. Okay, and how about this point? Well, this point is minus 1, 1. So then we have the vector field is minus 1, minus 1. Like that. Okay, so what is the circulation? Well, circulation in this case, F dot dr or d gamma, and so t is from 0 to 2 pi, f is minus y is sine t, so minus sine t, x is cosine t, and dr is minus sine t cosine t dt. So far, so good, everybody? Okay, and that equals dot product minus sine t times minus sine t is sine t squared. Cosine t times cosine t is cosine t squared dt. Oh, see, this is 1. So we have integral from 0 to 2 pi of t of 1 dt equals t evaluated from 0 to 2 pi. So that is 2 pi. Okay, so that's the circulation, because at each point, well, our vector field is going to in the same direction as the curve. So that's why we have a positive orientation. I mean, positive flow, okay, or circulation. Next, let's compute the flux. First of all, by looking at the picture, you can see all the vector field is going along the curve, in the direction of the curve. Then you can see the orthogonal component is gonna be 0, right? So we kind of expect we're gonna have a 0 flux. But let's calculate that. And so flux equals to Cf dot n ds. That is 0 to 2 pi f f is negative y is sine t, right? So negative sine t, x is cosine t. And then how about the n? Okay, so that is cosine t sine t dt. Okay, so that equals 0 to 2 pi, and we have minus sine t cosine t plus cosine t sine t dt. Okay, so that equals, oh, they're the same, so that's 0. Okay, yeah, we do have 0 floods in this case, because the you can see this vector field is going along in the direction of the curve. Okay, so the components going across the curve is 0. So far so good, everybody. And so in this process, keep in mind, okay, so keep in mind the formula for circulation or flow equals integral on the c f dx plus g dy, where f is fg and we have the velocity. Okay, we can think about the dr is like dx and dy. Okay, how about the floods? Well, floods is then the integral on c f dy minus g dx. So far so good, everybody. And in general, dr is not the t, okay? So be careful with that. So I would suggest you to use this formula. And in general, n is not, so in general n is not the dy and then minus dx. In general, they are not. In this example, they're the same because the speed is 1, right? The magnitude of the velocity in this case is 1, so we do have this n is in fact a unit vector, but in general this might not be a unit vector. Okay, okay, so what you do is you can just think about we can use f g dot product with this minus d dx. Okay, so in general, think about that. Okay, so but we know that this is like a velocity, and then they have the same direction. Okay, and these two they have the same direction, but they're not the same. Okay, just direction are the same, but the magnitude are different. We know unit tangent vector is the tangent vector divided by the speed. Okay, so that we get a unit vector, and the normal vector is kind of this guy, right? The cross product of t and k. Okay, so and this guy will have the same direction, but you probably need to divide it by the magnitude of that to create a unit vector. So far so good. So from now on, use this formula to calculate circulation and floods. Alright, so please go ahead and do your homework, and when you have questions, feel free to ask me. Have a nice day. Bye.